All right, let's get started. So last time we defined the complex number system, right? So today we're going to talk about polar form and more complex numbers, all right? So you know the deal. If we have x plus iy here, right? Then we can envision that in terms of, a triangle. Ooh, I was about to draw green on this board. That would have been somewhat silly. So of course the distance from the origin out to this point, I'll call it z, right? Is the length of z, right? We talked about that last time. Remember, the magnitude of z, it's the square root of x squared plus y squared, right? Remember? And so we can do a little bit more though, right? If this is the standard angle, theta, we know that this right here, x is equal to, and we usually call this r in like polar coordinates, right? So x is equal to r cosine theta, y is equal to r sine theta, right? And so what does this tell us about z? Z is equal to, well, x plus iy, right? But what's that equal to? That's equal to the magnitude of z, cosine theta, plus I magnitude of z, sine theta, right? Which we could, kind of light slipping through here. Man, that sunlight is bright, isn't it? Where's that coming from? Well, anyway. So we got the magnitude of z times cosine theta plus I sine theta. All right. And of course, you could write that as r if you like. So here's definition. E to the I theta is cosine theta plus I sine theta. All right. And what we're looking at here is the this is called the imaginary exponential. All right. So definition, if we have z equals to x plus iy, we can also write it as r e to the I theta, all right? And so this is the Cartesian form. This is the polar form. All right. So Cartesian form is unique, right? Like you give me a complex number, there's a unique Cartesian form. Polar form, well, you notice that so we know that cosine of theta plus 2 pi n is equal to cosine theta, right? And sine of theta plus 2 pi n is equal to sine theta, right? The period of cosine and sine is 2 pi, right? They're 2 pi periodic. And so you put these two things together, you get that e to the I theta, I times I plus 2 pi n, is equal to e to the I theta, right? So the imaginary exponential is also 2 pi periodic. Okay? And so like proposition, if we have e to the I theta, right, equal to e to the I beta, What's that tell me? So what that tells me is that theta minus beta is equal to 2 pi n for some integer n. So what did you guys learn in pre-calculus about the exponential function? Do you remember? A bunch of natural log stuff. Yeah, you learn a lot of different things, but one of the main things we teach pre-calculus students about the exponential when we're solving exponential equations is that it's got the one-to-one property, right? But the imaginary exponential does not have the one-to-one property. In fact, it is a little bit different, isn't it? It's got this, if you have two imaginary exponentials are equal, it doesn't mean that their values are equal. It means that their values could differ by a multiple of 2 pi. All right. Let me show you some examples of imaginary exponentials with numbers in them. So here's a good one. E to the, well, here's the first one. E to the I times 0, what's that equal to? That's equal to cosine of 0 plus I times the sine of 0. Cosine of 0 is 1. Sine of 0 is 0, right? So what do we got? We've got 1, right? So e to the I times 0 is also equal to 1. Another interesting one, if we do e to the I pi over 2, what do we get? That would give us cosine of pi over 2 plus I times the sine of pi over 2. Now cosine of pi over 2 is what? 0. Sine of pi over 2, well, that's 1. So e to the I pi over 2 is just equal to I again. All right, so if you want to, convert something to imaginary exponentials, these are useful facts, right? Like you can convert an I to an e to the I pi over 2 if you want.
Did they find this before Euler's equation or after?
Euler did this stuff in the 18th century. So in the 1700s. So like the notation I was introduced by Euler in 1777, but if I remember right. But Euler had the cosine theta plus I sine theta stuff, like 1740s, somewhere in there, or something like that. It predates the careful treatment of complex numbers by Gauss in the early 19th century. I would say it's really a bit of a stretch to say that Gauss invented complex numbers. I think it's pretty clear from Euler's work that he understood what they were both geometrically and algebraically. He may not have formally justified them like with a model like we did day one, but Euler knew what these things were. It's clear from his work. Cosine of pi plus I sine pi, what's that? Well, cosine of pi is -1, sine of pi is 0. So we get -1. And so from here comes the beloved formula, e to the I pi plus 1 equals to 0. So this one equation, a lot of people love this equation because it's got a pi, it's got an I, it's got a 1, it's got a 0, it's got all your favorite numbers in one beautiful equation. All right. So what are the properties of the imaginary exponential? So number one, as I mentioned in example 1, e to the 0 is equal to 1, right? That's an important one to notice. 2, if we have e to the I theta times e to the I beta, it's equal to what? Well, check it out. This would be cosine theta plus I sine theta, right? And this is cosine beta plus I sine beta by definition, right? So we can multiply those out. What happens? Here, I'll do it here. So we get cos theta, cos beta, minus sine theta, sine beta, plus I times parentheses cos theta, sine beta, plus sine theta, cos beta.
You get an identity on the left, an identity on the right.
Right? So trigonometry, we prove that this is cosine of theta plus beta. And by the adding angles formula, this is sine of theta plus beta. So just to write it down again, what we have is cosine of theta plus beta plus I times the sine of theta plus beta. Right?
And so you can just say e to the I, theta plus beta.
Yeah, this is, again, yes, by definition of the imaginary exponential, this is e to the I theta plus beta.
That's not how typical multiplication works.
Oh, no, that is like in real, I mean, that is how real exponentials work, right? If we just have like e to the x times e to the y, we do get e to the x plus y, right?
Yeah.
That's the usual. So this says that the law of exponents, the usual law of exponents for real exponentials generalizes to imaginary exponentials. But what's interesting here is in order to do it, we needed to know two of the fundamental truths of trigonometry, right? That the adding angles formula and the first cosine and sine are true, right? And also inculcated, built into the very sort of DNA of this whole discussion is polar coordinates, right? Like the whole definition of e to the I theta was motivated from just putting in polar coordinates for x and y, right? And sort of factoring out the radius, and whatever's left we're calling e to the I theta. Now this is a, I call it a transitory definition in the notes because we can define e to the I theta in other ways later in the course. But for our current purposes and just for calculational clarity, the definition for now for us is is cosine theta plus I sine theta. That's a good definition for e to the I theta. And as you can see, it has nice properties, right? 1 over e to the I theta, right? The reciprocal of it is e to the minus I theta. Right? The proof of that really just follows from 2 and 1, right? Because why? See, check it out. If I have e to the I theta times e to the minus I theta, what happens? You get e to the I theta minus I theta, which is e to the 0, which is 1, right? So because of this calculation right here, we get this identity over there. So this makes sense in part because the imaginary exponential is never 0, right? Check it out. E to the I theta is equal to cosine theta plus I sine theta, right? And what's the magnitude? I shouldn't say and, I should say thus. It implies that the magnitude of e to the I theta is what? It's the square root cosine squared theta plus sine squared theta, right? Also known as 1. But remember last time we proved that if the length of a complex number is non-zero, the complex number is non-zero. Therefore, e to the I theta is not equal to 0, right? For all theta.
Did they think about reproving trigonometric identities in the complex
I imagine part of what led Euler to, define e to the I theta like I've written here is precisely to prove things in trigonometry, because it allows you to prove things in trigonometry very nicely, right? Now, another way to see this, the reason that e to the I theta is non-zero, here's another truth that is good to know about. There is never a theta where both sine and cosine are simultaneously zero, right? Sine and cosine theta can't be zero for the same theta. All right. For e to the I theta raised to the n power is equal to e to the I n theta. So this can be proved inductively. I won't actually do the proof in here. It's a pretty simple induction. But that says quite a lot, right? Like this, if you expand this, what does this mean for n equals to 2, for example? So like cosine theta plus I sine theta squared, right, is equal to e to the 2I theta. What's that say? So this, of course, gives you cosine squared theta minus sine squared theta plus 2I sine theta cosine theta. I'll write it this way. Right, so that is equal to that. So you can equate, you can do what? You can equate the real part and the imaginary part. Every time we have a complex equation, that gets us two real equations. See? So we can equate this with this, right? And that with that. And of course, we get the well-known identities like sine of 2 theta is 2 cosine theta sine theta, right? And cosine of 2 theta is cosine squared theta minus sine squared theta. So these are, of course, well-known trig identities if you've taken trigonometry recently. They both easily pop out of identity 4, right? While we're on the subject here, since I've gotten this far, I should also mention that if we look at it, we've got e to the I theta is cosine theta plus I sine theta, right? And e to the minus I theta is cosine theta minus I sine theta. The reason that I say that, of course, is like cosine is even, so cosine of minus theta is cosine theta, and sine is odd, so like sine of minus theta is minus sine of theta. So that's why I get the minus in the middle, but not at the start. If you add these equations, what do you get? You get e to the I theta plus e to the minus I theta is 2 cosine theta. If you subtract them, you get e to the I theta minus e to the minus I theta is 2I sine theta. And so what that gives me then is stone-cold formulas for cosine and sine in terms of imaginary exponential. I get cosine theta is 1/2 e to the I theta plus e to the minus I theta. And sine theta is 1/2I e to the I theta minus e to the minus I theta. You can use these formulas and the properties of the imaginary exponential to derive a good chunk of what we memorize in trigonometry. Like, I'll just do one example of it, and then I'll cease and desist from this line of, jibber jabber. But example, did I do example yet? Example 2. Like if I wanted to figure out the identity for cosine squared of theta, right? I could take 1/2 e to the I theta plus e to the minus I theta. And I just take that and I square it. And I use the properties of the imaginary exponential to simplify, you know? And what that gives me is 1/4 e to the 2I theta plus 2 e to the I theta, e to the minus I theta plus e to the minus 2I theta, which, if you tilt your head and squint, well, these are inverses, right? E to the I theta times e to the minus I theta gives us 1. So what we really have here is 1/2 of 1 plus 1/2 e to the 2I theta plus e to the minus 2I theta. Notice I 2 over 4 is a half. That's what gave me the 1 there. And then the other 1/4 I rewrote as 1/2 times 1/2. The reason I did that is so that I can go, wait a second, that is just the formula for cosine theta, right? That's just the formula for cosine theta with theta replaced with what? With 2 theta, right? So what I have is 1/2 of 1 plus the cosine of 2 theta. So I hope you appreciate what just happened here. We have derived the trig identity for cosine squared by just plugging in the imaginary exponential version and seeing how the algebra works out. You can derive formulas for like cosine cubed or sine to the whatever just by this technique in algebra. So like it turns trigonometry into algebra. So I cannot overemphasize how beautiful this imaginary exponential is from an algebraic perspective. Like it's really, really neat. Yeah. Okay, so I begged a question last class. I asked, what's the geometry of the product of Z and W, right? So notice that, well, I'll start it over here. All right, so let's look at Z times W, all right, where now we are going to put Z and W into their like polar form, okay? So we're returning to the question of geometry of product. So if Z is equal to R e to the I theta, and W is equal to, let's say, S e to the I beta, right? In other words, you could say it's modulus of Z e to the I theta, and W is modulus of S e to the I beta, right? Fine. Then what is Z times W? It is, you know, R e to the I theta, S e to the I beta, which is what? RS e to the I theta e to the I beta. But what is that? That's RS e to the I theta plus beta. Or, you know, going back to the other notation, this is the magnitude of Z times the magnitude of W, right? So what do we see? We find ZW has length of Z times length of W, right? And angle theta plus beta. So when we multiply two complex numbers basically what it's doing is it's multiplying the lengths and it's rotating the number. So like, for example, if we had z is like 1 plus I, right? Let's see, how would you write that in polar form? Well, this is, yeah?
Yeah, so you take I and 1 and triangle it,
Uh-huh.
and so you square both, that'd be negative 1, 1, which would be 0. That does not make sense.
Well, the length of this is the square root of 2, right? Because that's 1 and 1. So like the length of z here is square root of 1 squared plus 1 squared, which is square root of 2. And this triangle, pi over 4. So here, z, we can write as square root of 2, e to the I,
How does that work out?
pi over 4.
It has to be 1.
Well, this distance is 1.
Yeah.
Square root of 1 squared plus 1 squared is square root of 2. Yeah. So the polar form of z is the square root of 2 times e to the I pi over 4. All right. Now, to illustrate the geometry comment I just made, let's see what happens when we multiply this by, what if we, let me try to draw it over here. Right? So if I think about the circle, bad, but anyway, this is supposed to be circle radius square root of 2, all right? So here's my z. If I were to rotate this by 90 degrees, right, where would it be? Like over here, right? So we should get minus 1 plus I if we rotate by, pi over 2. So check out what happens. If I do z times e to the I pi over 2, what happens? Remember, we worked out earlier today that e to the I pi over 2 is just I. It's just I. So this is 1 plus I times I, right? Which is I minus 1, as I predicted. So multiplication of a complex number by I rotates it counterclockwise by 90 degrees, or pi over 2 if you like. So it's pretty neat. All right, so I need to talk to you about arguments. All right, so definition.
You wrote something about
Pi over 2.
90 degrees?
That's 90 degrees, yeah. So let z be a complex number with z not equal to 0, all right? The principal argument of z is, let's say, theta naught, which is an element of minus pi to pi included, for which z is equal to modulus of z times e to the I theta naught. All right? We denote arg z equals to theta naught. In contrast, lowercase arg, all right, is equal to arg z plus 2 pi z. what I mean by that is it is the set theta naught plus 2 pi k such that k is an integer, right? If beta is an element of the arg of z, right, then e to the I beta is equal to e to the I theta naught plus 2 pi k, right? Which means that it's equal to e to the I theta naught in the notation of the definition above. So the argument is a set of values, right? It's an infinite set of values, but it's very special in its meaning. They're the set of values that if you feed them to the imaginary exponential, they all give you the same answer, right? What word do we use in trigonometry to relate, say, this beta and this theta naught? What kind of angles are those? Nope. You're getting there. Coterminal. Coterminal angles, right? So, fact. Z is equal to the modulus of z times e to the I arg z. There is a string attached. What do I need to say about z? Z is non-zero, right? We don't define the argument for 0. But for everything non-zero, we define the argument. All right? You work an example for you guys. Let's see here. Steal from my notes here. It's example 1.23. So here I have z equals to minus 2 plus 3i. All right? So notice that the length of z is the square root of 4 plus 9, square root of 13, whatever. Doesn't really matter, actually, right? And let's see here. It's good to draw a picture. Where is this? Minus 2 plus 3i. So z is like here, right? So if you calculate inverse tangent of minus 3, what? Well, there's a typo in the notes. I meant to have 3 over minus 2. Oh, I'm sorry. It's not. It's the typo is on the board. That's supposed to be. Oh man. Tell you what. Let's create a new example. Sorry, guys. The example that's fine in the notes. I'll let you read it. Let me just make something prettier for class here at the moment. Example 4. So suppose we had this one here. z is equal to, say, minus 2 minus 2i, right? So this is my z. What angle is that? The reference angle is pi over 4, right? Because this is a 2-2 triangle. But you've got this pi up here, right? So theta is naturally 5 pi over 4, right? But notice that this is not an element of, yeah.
Okay, so now we go into the coterminal.
We have to find the coterminal angle, which lies between minus pi and pi. That defines the argument.
Why did you put the pi up top?
Just geometric. Yeah, just to explain where the 5 pi came from. So this means that the argument of z is going to be 5 pi over 4 minus 2 pi, right? Which is minus 3 pi over 4. Which I think of geometrically as being this angle. Right? It's that clockwise 3 pi over 4, which is counterclockwise minus 3 pi over 4. So that's the argument. Now, little arg in this case is what? It's the set minus 3 pi over 4 plus 2 pi k, such that k is a integer. All right. So there are properties So if we have arg of zw, it's equal to arg z plus arg w. And what else can I say? I'm trying to remember. I guess that's the main one. But I should warn you that it is not true, right? But arg zw is not necessarily arg z plus arg w. So like the capitalization matters here. Let's see here. For example, if you had like e to the minus I pi over 2 times e to the minus I pi over 2, what would that give you? E to the minus I pi, right? So if my z and w are both equal to, e to the minus I pi over 2, what's the arg, capital Arg of z equals to capital Arg of w equals to minus pi over 2, right? But arg of zw is what? Here's where it gets fussy. Notice minus pi is not an allowed argument. So we have to find the coterminal angle to minus pi by adding 2 pi, right? So arg of zw is equal to pi. So you got to be careful. So in other words, we have to face the degeneracy of angles as we deal with these things, It's just the nature of the beast. I should mention that property 4 is called de Moivre's formula. I forgot to say that. All right. I don't know. I can't remember. Maybe not. What you will need in the homework for sure is the concept of the nth root, right? So let us discuss the nth root. So definition. let z be not 0 and n be an integer, positive integer, then the nth root of z is equal to the nth root of the length of z times e to the I arg of z over n. Now, I can derive this formula for you, explain to you where it came from. You know, it's basically the whole. Here's a short derivation of it. We're basically looking to solve that w to the n equals to z. We're trying to find a solution to that. Right? I mean, that's what you'd like to do. That would be what we mean. This is what we would hope for the nth root of z, right? So w would be equal to the nth root of z in this idea. So if w has like s e to the I beta, right, is equal to r e to the I theta, and that gives us s to the n e to the I beta n equals r e to the I theta. So when you're solving an equation involving polar form, think about it. It's really a two-dimensional vector problem, right? So for two-dimensional vectors to match up, they have to have the same length and the same direction. So the imaginary exponential really captures the direction. And of course, so this gives us two equations, is my point. We get s to the n equals to r, and we get e to the I beta n equals to e to the I theta, right? So what does this tell us? This tells us that s is the nth root of r, right? And this is ordinary garden variety real numbers, nth root, right? Because the r is a positive quantity, it's the modulus of z. But what does the second equation tell us? Yeah, this tells us that, well, it tells us a few different, let's see, it tells us that, I'm trying to find such w. That's my goal here. So I'm really trying to solve for beta. But of course, what this gives us is that this gives us that beta n is equal to theta plus some 2 pi k for some, right? We don't know. There's a lot of different things that can happen there, right? And so if we solve for beta, what do we get? Beta equals to theta plus 2 pi k divided by n. So what this shows us is that w is equal to the nth root of r, which remember is just modulus of z, right? And then e to the I. So we could, without loss of generality, we could just say that, well, that's the argument of z over n, right? Plus 2 pi k over n. Well, I guess I'll find L over n for some L. I don't know that L and Z are the same, right? I mean, L and K are the same. It could be that I didn't say that theta was the argument. If I said theta was the argument, then we'd have K equals L, all right? But the point is, this W is equal to e to the arg Z over n, right? Times e to the I times 2 pi L over n. where L equals to what? Well, if you look at it, L equals to 0, 1, 2, dot, 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 n minus 1 is all you really need to look at. See, because what happens when you get to n? Well, when you get to n, you're to 2 pi n over n, which is just 2 pi, right? So when you get to n, you're cycled back to what you got for L equals to 0. And as we let L go beyond this, we just cycle through the same answers again. So what you're looking at is a list of the solutions to the complex equation w to the n equals to z, all right? And so our convention is to call the 0th one of these solutions the principal square root. Excuse me, the principal root. This is called the principal nth root. All right? And so in contrast, if we talk about z to the 1 over n, that is equal to w in the complexes, all right, such that w to the n is equal to z. So notice we're going to make a distinction in the complex case between the radical notation and the fractional exponential notation. The fractional exponential notation is going to be a set of values, whereas the, so like here, this is specifically, you could write this as the nth root of z times omega sub n to the L power, such that omega sub n is e to the 2 pi I over n, and L is equal to 0, 1, 2, n minus 1. Let me show you so the definition, omega sub n, which is e to the 2 pi I over n, which of course would be like cosine of 2 pi over n, plus I times the sine of 2 pi over n, if we go back to, what that was. This is called the principal nth root of unity. So just to give you some basic cases, like if you put in omega sub 2, what do you get? E to the I pi. Remember we worked that out earlier? That is minus 1. Omega 3 is e to the 2 pi I over 3, which is less pretty, right? Omega 4, e to the 2 pi I over 4, which is e to the pi I over 2, which is what? Which is I. So just to give you an example, if we calculate the principal fourth root of I, that's the principal fourth root of e to the what? Pi I over 2, right? So that's just e to the pi I over 8, because the argument here is pi over 2. But I to the 1/4 includes e to the pi I over 8, and also I times e to the pi I over 8, and I squared times e to the pi I over 8, and I cubed e to the pi I over 8. See, in this case, this is omega 4, this is omega 4 squared, this is omega 4 cubed. This is actually really, really neat because it allows us to factor polynomials. So application, and I'll be done for today. Suppose I want z to the 4th minus I want to factor that, right? So a thing appearing in the factor should be a solution of z to the 4th equals to I, right? Z to the 4th equals to I, what are solutions to that? They're things in the 4th roots. They're 4th roots of I. So this is literally z minus e to the pi I over 8 times z minus I e to the I pi over 8 times z. I squared is minus 1, right? So minus e to the I pi over 8, and then z minus I e to the I pi, stupid board in the way, I pi over 8. There you go. We just factored this 4th order complex polynomial using the 4th root of unity idea. When you understand what these roots of unity do for you algebraically, you'll find that whole new doors are open for you algebraically. And we'll look more at this as we go on, okay? But so next time I should talk. I'm missing an I here. My bad. And this one's supposed to be I cubed, which is minus I. Oh, I'm sorry. Minus I. That should just be plus that, shouldn't it? Okay, plus and then minus I over here, right? Or plus I? Plus I, right? Yeah, I'm sorry. I've forgotten my factor theorem, right? You remember how it goes? F of c equals to 0. X minus c is factor, you know? I got to remember my minus. But anyway, that's still true for complex polynomials. But. All right, sorry I spent too much time on the cosine squared thing. That was my mistake.